so you can get the whole thing. So we're going to start with 2 questions that I've created from my Learn, Explain, Apply, Predict, so LEAP. So I used LEAP as part of one of my NSF grants that I submitted, and it's sort of you're learning something, then you're asked to explain it, then apply it, and then predict. So it follows the Bloom taxonomy. So that's where the LEAP comes from. So this is a fill-in-the-blank question, and you can answer in the chat. So again, anytime you see this iClicker, if we were in class, you would sort of get your iClicker out and answer it. So just answer it in the chat. So for in an SN2 reaction, the blank supplies a lone pair of electrons to attack the blank at a trajectory of blank degrees to the blank. So this is like organic chemistry Mad Libs, if you know what Mad Libs are. I always found Mad Libs fun. If you don't know what they are, maybe grab a Mad Libs from Books A Million or something and play with your friends, because it's pretty fun. So again, even if you see answers in the chat, I still strongly encourage you to put your own answer in. I know it can sort of be discouraging to see answers pop up pretty quick, but put your own answer in. With the iClickers, I reveal the answer after everyone sort of votes, so it's a little bit different that way, but. So yeah, the best response for this is C. So the nucleophile supplies the lone pair of electrons. So again, if you like sports, the nucleophile is sort of the quarterback. The lone pair of electrons, that's the football. So the football is thrown to the receiver, that's the electrophile. The trajectory of the lone pair of electrons when it attacks is 180 degrees to the leaving group. And again, the reason that is because you have the carbon bearing the leaving group is a sigma bond, then the anti-bonding orbital is 180 degrees behind that. So that's why we say there's a trajectory of the arrow. So any questions on that one? So these 2 questions are to see what your responses are. Again, these questions that look like I've photocopied them from something, I definitely have. So again, if we were face-to-face for Organic Chemistry 2, you would take a standardized test from the American Chemical Society. And this is from their study guide. So it says, which is the order from fastest to slowest for the rates for SN2 of these alkyl bromides. This first species is the nucleophile. DMSO is the solvent. We'll talk about solvent today. That stands for dimethyl sulfoxide. So you're asking basically a way to think about these. If these 3 were in a race, 1, 2, and 3, so just like a 100-yard dash, which one is going to win? Which one will be the fastest to react with this, the next fastest, and then the slowest? So Blakely, for SN2, the trajectory is always 180 degrees. For SN2, that's correct. So for these type of questions, you're making a comparison, and it says rate. So the first thing you're looking for, which one's the fastest? And so all these are sort of the same way, greater than. So there's no confusion there. The first number should be the fastest, and the last number should be the slowest. So my next question to you is, so you picked the right answer. So that's multiple choice exams, right? You're picking the right answer. But now I want to ask you the question of, what happened between you reading the question, you picking the right answer, what was the thought process to arrive at B as in boy as the correct answer? Why did you pick B? What was your reasoning? So your reasoning is the most important thing. So obviously you're evaluating all those criteria relative to something. So how did you evaluate that?
The way I was looking at it was the geometry of the molecules, which ones would have less hindrance to the backside attack.
So let me ask you a question. What do you mean by steric hindrance so that we all understand sort of what that term means? I'm gonna get very Supreme Court on you. Pretend I'm a lawyer and I'm interrogating you. What do you mean by steric hindrance?
I said B because with 2, the carbon that is receiving the substitution, it isn't bonded to as many other large atoms as in the other, as in 1 or 3.
So by steric hindrance, you mean like maybe van der Waals radii or size or bulk, sort of way of thinking about the three-dimensionality of the atoms around it, right?
Yes, sir.
So how do you classify substrate 2? How do you classify the carbon bearing the leaving group? So remember we talked about classifying alkyl halides? So Cole says the number of carbon attached to the atom in question increases this hindrance. Yeah, so what Cole wrote in the chat is correct. So if you think about the size of a hydrogen atom versus another carbon, as you increase the number of carbons around that, you're increasing the steric hindrance. The sort of evaluation, if you look at 2 is primary, 3 is secondary, and then 1 is tertiary. So that's really what we mean by steric bulk. Primary is less bulky, and as you go to secondary and tertiary, you're increasing the bulk. And as Aidan mentioned, the nucleophile is not able to access the electrophile through that specific attack trajectory we talked about. So if you can visualize, and I'll draw it on this structure here. This one, so this one, the antibonding orbital for that leaving group is directly behind. So this is the sigma star. It's got that little lobe in front. So the reason that 1 is the slowest is the nucleophile, which is supplying the electrons, it would have to basically go through that existing carbon-carbon bonds there. So its trajectory is impeded by these existing bonds. So for the primary case, not so much. The secondary case, you can see it does get a little bit impeded, but the only thing really impeding the trajectory are those diaxial hydrogens, but it can still do the substitution. So it's going to get in there because these are relatively small. So again, we're getting to the part of the semester moving forward that you need to think in 3D to understand bimolecular substitution, unimolecular substitution, and then the elimination manifold. So any questions on that one before we move on? So I have a little movie here. Again, so I've been studying this since for a very long time now, probably longer than you've been alive. That's the only advantage I have over you. I'm not smarter than you or blah, blah, blah. I just know ways to visualize things because I've been doing it longer. And again, to understand this stuff, it's sort of difficult because, like, when you're in the workbook, you know, these are like static images, but how you need to think about it is in 3D and things are moving. So maybe if this movie plays, I don't think it's going to, so maybe let me stop sharing this real quick and I'll open up my Keynote so you can actually see the movie. It's terribly Hollywood about it or anything. So can you guys see the movie? Can you see my Keynote? Okay, so all this is you're going to see basically showing you the promoting factors for SN2. And again, what we are learning now is, alongside learning reactions, we're learning the mechanism. And the mechanism is accounting for how the electrons move and how bonds are made and broken. So here we have our substrate, and X is a leaving group. The nucleophile supplies the electrons to the electrophilic carbon. This bond is cleaved. This thing in the square brackets here, this little equal sign with the slash through it, that's the transition state. We go from sp3 to sp2 hybridized. The transition state is non-isolable. What does that mean? So think of it as, so I have this chemical here sitting on my desk. It's from Oakwood. So this is a chemical. It's in an amber bottle. It's a powder. It's isolable. It's in here. I know it's in there. A transition state, you can't freeze time, isolate it, and stick it in a bottle. Remember we said when on this curve here, the transition state is the very top, and that's a fleeting moment, so maybe femtoseconds long. So once you're at the top of that peak, you either go back down to the reactants or you move forward to the products. So we're forming this bond, we're breaking that bond, we have our product, and then the leaving group. And so I have inversion of chirality, and what that means is everything on this face flips over to everything on this face. So the promoting factors are the nucleophile strength, and we'll talk about nucleophiles. Typically, most of them are metal salts. And what do I mean by that? Probably what you know most is sodium chloride. So sodium chloride, that's a metal cation, and then an anion. So for most of these, I haven't put the metal because the metal is purely a spectator ion. It's not incorporated into the product. Whereas the actual nucleophile, this thing is incorporated into the product. Notice most of them have negative charges. Some of them can be neutral though. The ones that are negative they'll have a metal cation balancing that negative charge. The substrate, Rx, that's the alkyl halide. So this is the classification scheme. Allylic and benzylic are greater than methyl, greater than primary, greater than secondary, and much greater than tertiary. So because we're learning reactions, we have to talk about solvent. Solvent is typically the liquid phase in which a reaction is run. So the solvent, it does a couple things. Number one, it solubilizes the substrate in the nucleophile. So things have to be in solution to collide and react. So if they're not in solution, think about two solids like banging together. They'll never react because they're not, in that medium to do so. The solvent is also a heat sink or a heat source. So if you need to supply energy to the reaction, you do it through heating the solvent, which in turn provides energy to the reactants to collide. In particular, for an SN2, we're using polar aprotic. Does anyone know what this word aprotic means? So we all know what polar means. Polar, again, is we have polarized covalent bonds. I'll write out what these solvents are in a later slide, but so yeah, aprotic means basically it's not a Bronsted-Lowry acid. So what does that mean? It doesn't have any hydrogens that are acidic or bonded to heteroatoms. So for example, let me show you. We saw DMSO. Organic chemists are fond of using these abbreviations, so you sort of have to know what those are. So DMSO stands for dimethyl sulfoxide, and that has the following structure. So that's dimethyl sulfoxide. That's polar aprotic. What is something that's polar protic? So ethanol, that's polar protic, and this is what the protic means, this OH. Notice in DMSO, dimethyl sulfoxide, there's no hydrogens bound to a heteroatom. So this is important because at the very end of this slide deck here, you're given a reaction and you have to diagnose the mechanism it's occurring by, and this is the part of Organic Chemistry 1 that students really struggle with, is because you're given the substrate, which is the alkyl halide, you're given the nucleophile, you're given the solvent, and then maybe you're given some temperature conditions. You have to look at all of that and predict what the product is. And you have to go through this flow chart or algorithm. Is it substitution bimolecular? Is it substitution unimolecular? Or is it elimination bimolecular, elimination unimolecular? So we're going to try to present this in such a fashion that you'll always be able to predict it correctly. Another promoting factor is the leaving group. So you need a good leaving group. Halogens or these things. And those things are basically alcohol derivatives that have the following structure. So this one that I drew is the OMS. And I'll explain what these other ones are on the later slide. But the leaving group X here, see how it's bearing a negative charge? The leaving group has to be able to stabilize that negative charge. And that's where we get back to the acidity in pKa. So our characteristics for SN2, we said the kinetics are second order, so that's what we mean by bimolecular. 2 is bimolecular. Second order, we have the rate constant. So this is the substrate with the leaving group, that's the nucleophile. Our stereochemistry, we have complete inversion. And I'll explain what rearrangements are when we talk about SN1. So rearrangements are not possible in SN2, but they are in SN1. Again, to make this as straightforward for yourself as possible, you really want to look at this thing first, the carbon bearing the leaving group, and classify it. Because after you classify it, then you're sort of making your decisions easier. It can go SN2 or SN3 based on that classification. This is your free energy reaction coordinate diagram. Again, we talked about that. You have your starting materials at some energy. You're going up to a transition state, which is higher energy because you're changing hybridization. And then you can go down to the products. If you go down, delta G is negative. If this value is a little higher than what you're starting with, it's going to be positive. So it can be either or. I'm just showing you one case. Any questions so far on that? So non-isolable means you basically you cannot isolate it. It is impossible to like hold it with your hand like I'm holding this pencil. You can't isolate it. The length of time that it exists is so fast, it's fleeting. So I want to run through some notes here and talk about the kinetics a little bit more so that we can understand the bimolecular aspect of this. So I said the rate is equal to the rate constant times, and I'm gonna use the specific example we were talking about. So we have our rate constant times, what do the square brackets mean again? Can anyone refresh my memory? So it's concentration in what unit? So it's molarity. And what is molarity again? So moles per liter. So you'll typically see things written like that, but also you might see sometimes it's written like that. And this sort of always, when I was a student, that sort of bothered me because I like looking at things like this. It's easier for me to understand. So here they're showing it as a quotient, and here they're showing it as a product. So the moles times liter to the -1. Just understand that this -1 really just means 1 over liters, but you might see it represented that way. So the rate constant has the following units. So K is your rate constant. So that has units of liters per mole second. And again, alternatively, you might see it like that. Apologize for my sloppy handwriting. So overall, the rate is going to have the following units: liters per mole per second. So if you plug this into here and here, then this here, ultimately these are the units for your rate.
Wouldn't it be moles per liter second, or do I have it upside down?
You are correct. I'm looking at my screen, I'm looking at the chat, I'm looking at my notes, and I wrote the wrong thing down from my notes. So I'm gonna do a little erase here. Thanks for pointing that out. So yes, it is, the rate is moles per liter second. That's correct. I was focusing my eyeball in the wrong place. So why am I bringing this up? Why am I harping on this? So let me show you some substrates, and then this will get back to reinforcing the thing about classifying. So substrate. Then over here, I'm going to put relative rate. So in this course, since there's a lot of different types of majors, we really talk qualitatively. And that's sort of where the relative part of this comes in. You're always comparing two things. So if you're in polymer science, you eventually go on to take a class called polymer organic chemistry, and you're really going to dive into this stuff more thoroughly. But for now, we're really just considering the qualitative things. So let me put this substrate up. This is methyl bromide. So this has a relative rate of greater than 1,000, and as you see as we go down this column, you're going to see one of them is benchmarked at 1. And so that's what we're talking about. So all I'm going to do as I move down here is I'm going to just substitute out hydrogens for carbons or methyl groups. So this is ethyl bromide. This is 50. Now the next one I'm going to draw, I'm substituting out 2 hydrogens for 2 carbon or 2 methyl groups. So this is isopropyl bromide. So this is our benchmark of 1. So is everyone clear on what I mean by benchmarking? If you're into like computers, they do this a lot. It's so that this, we're talking about the rates. So isopropyl bromide, this is a secondary substrate. we're going to benchmark it at a rate of 1. So compared to ethyl bromide, which is primary, ethyl bromide reacts 50 times faster than this. Methyl bromide, so it's methyl, it reacts 1,000 times faster. Let's look at the tertiary substrate. So all three are substituted now. So this is tert butyl bromide. Now this one is much, much slower. So again, the reason for that is as you think about the size or van der Waals radii of a hydrogen versus a methyl group now, you're increasing that bulk. And so really what we're looking at is the access to that sigma star orbital. So here it's pretty easy, but we're increasing the bulk. And when we get to tertiary, these methyl groups are basically within the vicinity of that sigma star, so the nucleophile cannot attack that carbon. So I don't want you to get complacent and think, well, it doesn't react by SN2, I can forget about it. But you can't, because tertiary substrates will still do substitution. They will not do it through this rate equation, though. So see this rate equation? A tertiary substrate will react through SN1, where the 1 stands for unimolecular, and that deals with the concentration of the substrate only. So tertiary substrates do substitution in a polar fashion, but the mechanism is different. And so again, SN2 versus SN1, we're talking about the mechanism. Any questions on that before we move on? And again, in this screencast, we're looking at the factors that promote substitution reactions. So again, I hate to sort of use the medical field as the go-to career choice, but a lot of you are pre-professional, either medical, pharmacy, vet, dental, whatever. And this concept is relevant to you for diagnosing a patient or an animal or whatever. You know what I mean? If the patient comes to you and complains of these symptoms X, Y, and Z, you have to diagnose, okay, it could be COVID or it could be the flu. So that's how this is relevant to you, is synthesizing information to make the best choice. So here all I've done is I've got some pictures from your workbook. That's what we'll do in these next couple slides, so we'll try to make this interactive. This is from chapter 9, substitution reactions. This first one's on page 148. So it says, identify whether each of the following substrates is more likely to participate in SN2 or SN1. We haven't talked about the mechanism of SN1 yet, but you know how to make this decision. So this is a decision point. So I say evaluate classification of leaving group. So basically, you're finding in the molecule, which carbon atom is bearing the good leaving group, and then you classify that. So for 9.2, how do you classify this alkyl halide? Is it primary, secondary, or tertiary? You can put your answer in the chat. So it's secondary. Based on that information, how do you decide? Is it SN2 or SN1? So Aiden says, couldn't it react both ways? So it can. And so this is a perfect example, as I told you, from an instructor point of view, if I had to project why students struggle at this point in the semester, it's that sort of answer. Because you as a student want to know definitively, it's going to be this or that, not both. And so the secondaries can react either through SN2 or SN1. And so what do you have to do after that? Then you have to look at the reaction conditions. And then you make a further decision point where you ask yourself a question. Is the nucleophile strong or weak? Is the solvent polar protic or polar aprotic? So you have to ask all these other questions, and then eventually you're gonna make a decision. It is SN2, it is SN1. But right now you really can't definitively say. So let's look at 9.3. Here's our leaving group. How do you classify that leaving group? So this is primary. So primary is going to be what? What mechanism will this occur by? So primary is SN2. And right now, you do not have all of the information to understand why it cannot react by SN1, but eventually you will. So again, we're on this spectrum where we have to evaluate the classification of the substrate and whether it's going to go SN2 or SN1. So primaries always go SN2. What about 9.4? What is the classification, and then what is the mechanism type? So I would say this one is secondary. So we're in the same sticky wicket here. So these, again, we have to evaluate other factors other than just the classification of the leaving group. So what about 9.5? What's the classification? So 9.5, we have a carbon-iodine bond. That's a good leaving group. What's our classification? So it's tertiary. And tertiary has to be what? So the mechanism of substitution is SN1. So just, I know I'm harping on this, but the 2 means bimolecular, such that in the rate equation, you have the concentration of the nucleophile and the concentration of the electrophile. The 1 is unimolecular, so that only the concentration of the electrophile matters. Now let's go to these next problems, 9.7 through 9.10. For each compound, determine whether loss of the leaving group would result in a resonance stabilized carbocation. If you are not sure, try drawing resonance structures of the carbocation that would form upon loss of the leaving group. The first thing I want you to do, even though we haven't specifically talked about this, is classify the carbon that is bearing the halogen. What I mean by classification is the hybridization. So for 9.7, what is the hybridization of this carbon? Now let's just do that for all of these because I want to make some very general statements before we get into the actual meat of the question. For 9.8, what is this hybridization? So sp3, 9.9, this hybridization, sp2, and then finally 9.10, the last one is sp3. So now I'm going to make the following statement, which is going to clarify how you answer this question. sp2 hybridized carbons do not undergo substitution, which answers the question by saying 9.7 and 9.9 cannot ionize to form carbocations. So I know we're still talking about SN2, but I want to just show you I want to include this at this point so you sort of have an understanding of what SN1 is and why it's different. So 9.8 is sp3 hybridized, so that can ionize, as well as 9.10. So I want to say, actually I don't want to say that. So we'll just say they're hybridized, and let me go ahead and show you how they ionize, what I mean by that. So is everyone comfortable with how I assign delta minus, delta plus? Actually, oh, sorry. So when we say ionize, that means we are going to cleave this bond. We're going to cleave it, in this case, heterolytically. So hetero means different, right? Lytic means cleavage, lysis means cleavage. Heterolytic means different cleavage. So that bond is cleaving differently. And again, this is different from homolytic cleavage, which we saw in chapter 10, which was radicals. So the bond will cleave so that the carbon or the atom bearing the partial negative charge gets both electrons in that bond. So I've cleaved them. We've done heterolytic cleavage. What charge should I write here on this carbon? And what charge should I write here on that chlorine? So in the chat, you can say carbon equals, chlorine equals. Carbon is plus, chlorine is minus. So it says to draw some resonance forms for that. And again, so now we see an actual plus charge. I'm going to put 1. I'm going to put a 2. I'm going to put a 3. You'll notice that plus charge migrates to from the 1 carbon to the 3 carbon through the following arrow pushing. So that's an exercise in drawing those resonance forms and showing you polar ionization. So that's part of SN1, which we will study more in depth. But any questions on those before we move on? So what I want to talk about now is the nucleophile strength. And so let me show you I guess what I can do is I'm just going to write to this table here. And this shows you the different types of nucleophiles. So again, there's a lot of them shown. And the gist of this slide, your substrate or electrophile that's bearing the leaving group X. Your nucleophile, which is a Lewis base, is supplying the electrons. You're substituting the leaving group for the nucleophile. That's how you get your product. And then you have your leaving group X minus. Why do we learn these reactions and mechanisms? So in this first column, you have your alkyl halides, chlorine, bromine, iodine. Notice I've just put Rx. I haven't put anything with like classifications, but again, methyl primary or secondary are all valid substrates. These are different nucleophiles. So let's take this first row here. Say you have some alkyl halide that's chlorine or bromine, and you're treating it with I minus. What that's going to do is substitute the chlorine or bromine for iodine to give you an iodide. So what you're ending up with in the product is an alkyl halide. and this is called a Finkelstein halide exchange. So there's reasons why you'd want to substitute a chlorine for an iodine in synthesis, and we'll eventually learn those things. So the second one here, again, what's changing is these nucleophiles. You can start with an alkyl halide. If you treat it with, say, sodium hydroxide, you end up with an alcohol. That's the functional group. What I haven't shown in here, and what's important to recognize, these will typically have some metal cation that's balancing out this negative charge. The metal cations are typically, again, depending on stoichiometry, lithium, sodium, potassium, or again, you can have magnesium, the divalent metals, they can be in there as well. But again, they're the metal cations are spectator ions. Again, what I mean by that is they're not incorporated into the product. If you had OR, say sodium ethoxide, that would make an ether. So when you look at this column here, functional group, think about when you're taking an alkyl halide, reacting it with a nucleophile to get these sort of functional groups. What form of spectroscopy could you use to determine if the functional group was incorporated into the product? So remember the types of spectroscopy we learned? Which one is good for functional groups? So Mac and Cole say IR. That's exactly right. So when you want to determine experimentally, did the reaction work? You can go take an IR and look for those specific stretching frequencies at the regions 1, 2, and 3 to see if the reaction actually worked. So again, organic chemists use a lot of abbreviations. These names you see, these are the scientists that discovered those reactions. So in a sense, you sort of do have to know them. If we say a Gabriel synthesis, that's specifically referring to an amine. A Williams synthesis is specifically referring to the formation of an ether. So again, these are all good nucleophiles. If you use SH, that gets you a thiol. Again, a thiol is the sulfur version of an alcohol. SR, that's a thioether or a sulfide. Ammonia gets you an amine. Azide gets you the azide functional group. You can have carbon nucleophiles. So an alkyne gets you an alkyne nucleophile. Cyanide gets you the nitrile. This acetate gets you an ester. You can have neutral nucleophiles to get phosphorus. That gets you a phosphonium salt. That's important for organic chemistry too. Again, the SN2 reaction is basically taking an alkyl halide and making some other functional group that you've already learned. So let me click over to this next slide. We have some time to answer this. It says, identify whether each of the following nucleophiles will favor SN2 versus SN1. So, as we saw in the prior slide, SN2 nucleophiles, again, typically have a metal cation, and then the nucleophile is negatively charged. SN1 nucleophiles are typically neutral. So the diagnosing factor for SN1 is that the nucleophile is typically also the solvent. And again, I know you can't learn everything at once, and I'm giving this to you in little dribs and drabs, but if I sort of just dump the bucket on you, it might overwhelm you. So let me write M plus nuc minus. So just knowing that information, how do you diagnose 9.12? This nucleophile ethoxide. Is that an SN2 or an SN1 nucleophile? So it's SN2 because we see that negative charge. It's the negative charge. Again, typically a counterion for that would be sodium. Sodium ethoxide. How do you make that? You pour ethanol into your flask. You throw in little cubes of sodium metal. The sodium metal dissolves. That forms the sodium ethoxide. So what about 913? What do you think, SN2 or SN1? So again, there's no charge. It's neutral. That's SN1. As we see with the next one, ethanol. So here's another diagnosing factor when you have to make the decision SN2 versus SN1. For SN1, the nucleophile is typically neutral, and it's also the solvent, so it's dual purpose. I underline typically because I remember I'm sitting on the Supreme Court, covering all my bases. Typically, I'm not committing one way or another. So I'm sort of lawyering you at this point. So what about 15, 16, and 17? What do you think? What mechanism should those occur by? Again, we're diagnosing the nucleophile. So these are all SN2. They're all bearing a negative charge. Bromide, hydroxide, cyanide. So just as a refresher, the IDE ending, typically, again, I'm CYA here. Hope you know what that means. Typically means negative. So that's your Gen Chem nomenclature. So you could have potassium, bromide, lithium, hydroxide, sodium, cyanide. Those are the spectator cations that balance that negative charge out. That's what you go to the shelf, you pick up that bottle of potassium bromide. That's what you actually weigh out. So we're about out of time for this lecture. Below you, we'll go through diagnosing factors of the leaving groups. So if we have a molecule that has two leaving groups, which one's better and why? Some more of those. And then this is really at the end of that chapter 9 in your workbook. This is where you really have to put all of those promoting factors together. The nature of the substrate, the nature of the nucleophile, the nature of the solvent, which mechanism occurs, what sort of substitution happens. So that's what we're ultimately aiming to do in this module. So with that, I'm going to go ahead and end it, and stay safe out there today with the hurricane blowing through.